So let's just talk a little bit more about quantization of light a la Einstein, meaning Einstein said light comes in packets. They're called photons, and they're like particles. They have energy equals hf. And just for notation's sake, often, certainly I will, and you will see other people do, right? If we've got a particle, you've got a particle moving at speed v. If you've got a photon, we call it a gamma. For whatever reason, that's the abbreviation of a photon. And we often show its motion as a wave motion in order to indicate that it's light. But a gamma is like a photon moving at speed, well, it would move at speed c. Or you could draw this moving at speed c, but the gamma indicates a photon. That's just an image of a moving particle. So we're going to see when we move on to the next section, when we talk about the collision of light with particles, you've got a particle moving at speed v, and you've got a photon moving at speed c, and those two collide like two particles, and we'll look at the energy and momentum in that collision. But that's not what we're talking about right now. All light has this property, and indeed it has been proven that this is a correct picture of light, that we can treat light like a particle, just like you can treat particles like waves, which we've already implied. So let's just do an example talking about the sun. And the sun is an orange yellowish ball that when we're children, we draw it with, I guess, indicating there's sort of rays coming off of it. There you go. The facts about the sun is that we have measured that the power of the sun is approximately 3.74 times 10 to the 24th watts. Remember, think of like a 100-watt light bulb that you have in your house, or a 10-watt light bulb. So this is quite a bit bigger. The sun is bigger than a light bulb. And that lambda max, the peak wavelength that comes off the sun, is somewhere in the yellow, orange, blue, so I don't know, in the middle of the spectrum, about, let's just say 500 nanometers. And let me just ask a question. How many photons per second hit the Earth from the sun? So again, notation, this is photons per second. Okay. How are we going to figure that out? Well, let's think about it. The energy of a photon is h times f. And we know that the frequency of the sun is, or at least the average frequency is hc, or f is c over lambda, hc over lambda. And so we can go ahead and say, oh, that hc we know is 1.2 times 10 to the minus 6 eV meters. And as a matter of fact, here we've got MKS units of power, so we are actually going to want to put this in MKS units probably eventually, or one or the other, but right now we're mixing our units. Okay, and lambda is 500 nanometers, so the energy of a single photon coming from the sun is 2.4 eV. It's a single energy of the single photon from the sun. So how do we turn that into photons per second? Well, hopefully you get that. Power is energy per second, so since the power is 3.74 times 10 to the 24th joules per second, therefore, how are we going to figure out the number of photons per second? If a photon is a certain number of joules, let's say a photon was 1 joule, then this would be 3.74 times 10 to the 24th photons per second, right? So it's just P over the energy of a photon is equal to the number of photons per second. Not a quantum mechanical fact. That is a dimensional analysis. You should see how to turn, if you know the energy of a photon and you know the energy per unit time, you should be able to figure that out to the number of photons per second. Think about it. So that ends up giving us 9.7. I changed the units to joules here. Changed the electron to a coulomb. 9.7 times 10 to the 42 photons per second. So there are 9.7 times 10 to the 42 photons per second coming from the sun. That's an unimaginably large number. But that is not the answer to the question. The question was how many hit the Earth. Keep in mind this picture is not to scale. Hopefully you know that. You got the sun, you got the Earth going around the sun, and all those photons are going in all directions through the sphere, right? Through this sphere that is made up of the radius from the Earth to the sun. and the Earth subtends just a small bit of that angle, right? It's a two-dimensional subtended angle. So what we need to do in order to figure out the number of photons that hit the Earth, what do we need to do? Can you figure it out? You can pause and think about it for yourself, but we need to take the surface area. It's the fraction of the cross-sectional area of the Earth, right? Cross-sectional area of Earth divided by the area of the sphere, which is made up of the radius from the sun to the Earth. That's the fraction of the area of that sphere that the Earth takes up, and that's the fraction of the photons that are going to get caught, because the rest of the photons are all going, well, let's see, what color was the photon? Oh, right, the photon is approximately yellow, right? So the photons are going that way, and they're going that way, and they're coming out of the page, and we just can't draw in 3 dimensions. Only some of the photons are hitting the Earth. These are the photons, these are the photons, these are the photons, all having fun. So this is the fraction that tells us how much of that area is subtended by the Earth, and the radius of the Earth is 6.37 million meters, and the distance of the Earth to the Sun is 1.5 times 10 to the 11th meters, and you can do that out to find that that is equal to, that fraction equals 4.5 times 10 to the minus 10. So the number of photons that hit Earth is 4.5 times 10 to the minus 10 times the number of photons that leave the Sun, which is 9.7 times 10 to the minus 42. So getting 4.4 times 10 to the 33 photons per second, still quite an unimaginably large number, but yeah, we get a lot of light from the Sun. Now let me ask how many of those, let's say you look at the Sun, which you're not supposed to do, absolutely not supposed to do, but all of us have sort of done at some point in our lives probably. Approximately how many photons per second do you get in your eye? So that's easy enough. You just, instead of, right here, instead of putting the area of the Earth, you can just put the area of your eye. And approximate the area of your eye, I don't know, 10 to the minus 2 is the, 10 to the minus 4 square meters, 10 to the minus 4 square meters or something like that. And I'm not going to do it out, but the result that I want to show you is that if you look directly at the Sun, you get about 10 to the 16th photons per second in your eye. 10 to the 16th photons per second. And I'll tell you, that's a lot of photons. You could figure this out for a light bulb. It would be easy enough to do for a light bulb. You could figure that out. See, there's certainly a lot less. But what's particularly interesting is that, you shouldn't be looking at the photon for too long. You can look for the Sun. You can look at a photon as long as you want. Shouldn't be looking at the Sun for too long because this amount of photons, this amount of energy will do damage to your eye. But we've all probably looked at the Sun directly for a second in our life or longer. So 10 to 16 photons, and you can see the Sun, and it kind of sears an image into your brain. But anyway, the point that I want to make is that experiments have been done which show that your eye can be sensitive to a single photon. In other words, you can see a single photon. And it's just kind of unimaginable, right? One photon versus 10 to the 16th photons. Is that your eye is that versatile, right? That it can see a single photon. It can also take a 10 to the 16th photons without destroying it. So it's just an interesting that our eye has indeed evolved to be such a good vision instrument, even though some of us have problems with our eyes. Okay, moving on. We're going to move on to the last part of the chapter, which is about X-rays and colliding X-rays with electrons. X-rays, which are also photons.